can avoid high reluctance at the joint where laminations are built against each other. Okay. In actual transformer construction, primary and secondary windings are interleaved to create or reduce some leakage flux. Okay, so reduce the leakage flux, and current is flowing through these strips. Okay, when current is flowing through these strips, if you are not providing some good insulation up in these two plates, then this particular current will flow through the another plate. Okay, so it will create the leakage flux. Okay, core type of a transformer, or we can call it as L shape type of a transformer. The shell type of a transformer, you have to cut the material in E and I type of shape. Okay, in case of cell type of a transformer, each lamination is cut in the form of long strips of E and I shape. Okay, in a shell type of a transformer, the core has three limbs. The central limb carries the whole of the flux, whereas the side lobe carry the half of the flux. Core. Okay, this portion is called core. This is the core type of a transformer. This side of the transformer is called primary, and this side of the transformer is called secondary. Okay, so here you are applying some voltage, that is AC voltage you are applying, and when you apply AC voltage, some current will flow through this particular wire. Okay, you know this wire act as a coil right here. Okay, if you place some wire across some material like coils, if you place some material inside this particular coil, some magnetic field will be generated. Okay, so those magnetic fields will generate electromotive force. Okay, EMF will be generated right here. Okay, so that particular EMF will generate the flux across these windings. Okay, so this flux will flow through this particular material from primary side to the secondary side. So in inductor, what will happen? This, let's suppose that this is your current and this is your voltage. This current lags voltage by 90 degree. Okay, AC alternating current, and this current will flow through this particular inductor, or we can call it as a coil. Okay, when current is flowing through this particular coil, magnetic flux or alternating flux will be generated right here. Okay, in this core, so we can call this as a core. Okay, and here what will be generated right here? Here magnetic flux will be, or mutual flux, or we can also call alternating flux, will be generated right here. Flow from primary side to the secondary side. Okay, but due to the self inductance, this E1 EMF, this is your self induced EMF, will be generated right here. So this self induced EMF should be equal to the generated flux by this particular primary side to the secondary side. Okay, when this particular flux and self-induced will match with each other, this particular flux is going to flow from primary side to the secondary side, and this self-induced EMF across secondary side will be generated. This is the complete time period. Okay, this is represented by T, and from the high position of this first to the lowest position of this second, it is represented by half of F. Okay, so what is this? 1 by 2 into F. What is F? F is the frequency. F is equal to 1 upon T. Okay, okay. So in transformer, the induced EMF in primary and secondary winding depends the rate of change of flux linkage. It will depend upon the number of turns and rate of change of flux with respect to the time. Okay, so this is the mathematical formation in transformer. Okay, so in the primary side, what are the components? Quickly give your response. E1 is the induced EMF in the primary, that is directly proportional to the number of turns. Okay, that is N1. So this E1 is the EMF and N1 is the number of turns. Okay, so if you increase the number of turns right here, more EMF will be generated in the primary side. Okay, if you use less number of turns in the primary side, less EMF will be generated in the primary side. Now construct the same formation for the secondary side. So in the secondary side, what is your EMF? E2. So this E2 is directly proportional to the number of turns in secondary side. Okay, so this is again EMF for the secondary side, and this is the number of turns in the secondary side. So in the secondary side also, EMF is directly proportional to the number of turns. If you increase the number of turns, more EMF will be generated across the secondary side. If you decrease the number of turns in the secondary side, less EMF will be generated across secondary side. Step up, as you know, secondary side, this is N2 and this is primary side N1. Okay, so primary voltage is less whereas the secondary voltage is higher. Okay, so it is step up transformer. Number of turns in the secondary side is less than number of turns in the primary side. We can call it as step down transformer. Transformer ratio. So what is transformer ratio? Secondary voltage divided by the primary voltage is the transformer ratio. The direction of the induced EMF is opposite to the applied voltage V1 according to the Lenz law. From this Lenz law, we derive this particular statement. Okay. What is ideal? Ideal means it will give you 100% output. Okay, there is no loss in the output, there is no loss in the efficiency. Okay, so this ideal transformer, let's suppose that it has no ohmic resistances, no magnetic leakage flux. Okay, so if there is no resistance or no ohmic resistance or no magnetic leakage flux, all the flux produced in the core link with the primary as well as secondary. This transformer has no losses. Let's suppose that there is no copper loss, no iron loss, no core loss. Okay, such type of transformer is called ideal transformer. There is no power loss, therefore output must be equal to the input. Okay, so we can write directly output should be equal to the input. Okay, output should be equal to the input in ideal transformer. There is no ohmic resistance. Okay, there is no magnetic leakage flux. Okay, there is no copper loss, there is no iron loss or core loss. Okay, no leakage is there. Okay, so your input or your output should be equal to the input. You can write it E2 is equal to V2 or E1 is equal to V1, and put all these value in this equation. So V2 upon V1 is equal to E2 upon E1 is equal to N2 upon N1 is equal to I1 upon I2. So this is equal to K. So K is your transformer ratio.